Okay, I'm going to derive the Schrodinger equation, which is one of my favorites, and talk a little bit about why it's important, but more importantly for now, just show you the math on how it came about from all of the physics and math that it started from. So we begin with this classical equation, and it looks like this. So all that this is an amplitude equation, and it's the equation of a wave with spatial dependence and with time dependence. And the spatial part is some wave function which we want to determine that defines its movement in space. And then if it has time dependence, then it's just a cosine function in this case. So this is the frequency of the vibration of the wave. This is the time at the point that you're observing, and this is the coordinate that you're observing. So in one dimension, we consider it kind of like a rubber band. If you have a rubber band and then you pluck it and you observe its movements in time, you would be looking at only one spatial component, which is the x value. So it's how far is it from its original flat line, horizontal line, and as it moves in time, it'll change. So at one instant in time, it might look like that, but in the next instant, it may look like that or something, and it will keep kind of vibrating, and over time it'll actually dissipate in the case of like a simple rubber band. So that's kind of what we want to model with the wave equation, but it's for not just rubber bands but any particle. Okay, so that's the generic form, and then we move forward with the classical wave equation, which tells us how the time and space components are related. So it says the second derivative of the function with respect to the position is 1 over the velocity squared times the second derivative of the time component. So space and time are related by this inverse square of velocity. That's how it works. And so now all we do is plug in the value for u here for the function right there. So we want to look at our specific example for the wave equation. And so that is this space and time component with respect to x. The second derivative with respect to x. And now we have with respect to time. And that's it. So taking the second derivative of this thing with respect to x means that this part remains a constant because there's no space dependence, there's no x dependence, it's only here. So we can just pull it out like any normal derivative, like that. And we're left with this. And then on this side, we want the time derivative, so there's no dependence on this spatial component. So that can come out. And then we take the second derivative of cosine. So the first derivative of cosine is minus sine, pulling out the omega, right? And the second derivative would be the minus cosine, pulling out another omega. So you end up with omega squared, pulling it out twice. You end up with a minus, and then you have sine omega t, for second derivative of cosine omega t, right? So that's where we are currently. At this point, that's cosine. At this point, we can divide by cosine omega t and just get rid of it to simplify, which is useful. So we're left there. So now we have this form, which is pretty simplified. All I'm going to do is move this part to the left. And I'm also going to change this notation to the simplified double prime notation for derivatives, just like that. So that's the second derivative with respect to x. And I'm going to add 1 over v squared psi of x omega squared. Okay, so this is where we are now. We have omega squared, and then we have the velocity squared, but these can be related to simplify things. So we remember that omega squared is a frequency squared, And remember that omega is nu times 2 pi, because this is a radial frequency and this is a normal frequency. So omega squared is simply this squared, which is simply nu squared 4 pi squared. Right? Okay, so that's that part. Then we remember that a velocity has units of meters per second, which is like a distance divided by time. But we want to relate to frequency, which is simply 1 divided by time. So to get that, we could simply take velocity divided by some distance, like a wavelength, and get units of 1 over time. Those are the units. So the units being 1 over time, that works because you have meters per second divided by meters. That's just 1 over seconds. So this velocity over wavelength is itself a frequency. So this is itself a frequency. And the only thing left to recall is that this frequency is related to omega, pretty simply, by a factor of 2 pi. So now we have v squared over omega squared is nu squared, simply. So, and then v squared equals nu squared times wavelength squared, lambda squared. So there's our new velocity, and then simply velocity squared is nu squared, which is omega squared over 4 pi squared, lambda squared. So we just replaced nu with omega squared over 4 pi squared. Nu squared with omega squared over 4 pi squared. Boom. So this is velocity squared, just relating units and things. Then we have this as a new result. So 1 over velocity squared becomes 1 over this. So we have 1 over lambda, 4 pi squared on the top, omega squared on the bottom, psi of x, omega squared is 0. So all we did here is replace 1 over v squared with the inverse of this. That's the inverse of that. And now we arrive here. Almost there. You can cancel omega squared quite easily right there. It just goes to 1. And now we have a new simplified form. The second derivative of the wave function is 1 over lambda squared, 4 pi squared, psi of x, and that's equal to 0. That sum is equal to 0. Okay, so now we introduce the quantum mechanical addition, and that comes in the form of the de Broglie wave, which, if you remember, you may have learned like in general chemistry. It's simply that the wavelength of particle in motion is Planck's constant divided by the momentum. So it's a very simple relation. So we're going to use this to get to our quantum mechanical form of defining the motion of a particle. So here we have lambda squared in our equation. We have lambda here from de Broglie, so let's just make it squared, simplify things, squaring everything. Then we want the inverse. So the inverse is simply this. Okay? And so we're going to replace that in our equation, remembering, though, that momentum can be described in terms of energy. So we have momentum here, and I'll go ahead and put that first to clarify. So now our form is psi of x double prime plus p squared over h squared 4 pi squared psi of x equals 0. Okay? There we are now. Now let's look at momentum in terms of energy. So we remember from Newtonian mechanics, energy is always described as a potential and a kinetic component, or you might be more familiar with this potential component. Potential and kinetic energy is total energy. And then we also remember that kinetic energy is described by 1/2 mv squared from Newton's equations in kinematics, from calculus with the motions of particles. But then we also remember, this is one of the most useful little tricks to get you familiar in quantum mechanics, that kinetic energy can also be described by momentum squared divided by 2m. It's very simple, but a lot of people don't realize it at first, because you remember momentum is mass times a velocity, so momentum squared is mass squared times a velocity squared. And then if you want to get 1/2 mv squared, all you do is take this quantity, divide by m, well there's your mv squared, and then you divide by 2, and there's your 1/2 mv squared. So p squared over 2m is in fact equal to 1/2 mv squared. And so that's why I can write this equation for energy. Now all I want to do is express, instead of energy in terms of momentum, momentum in terms of energy. So just do a little bit of algebra, and you end up with E minus V is p squared over 2m. Then you end up with 2m times E minus V is p squared. And then finally, to simplify, p is the square root of 2m E minus V. So there's that. That is momentum in terms of the energy. So we're going to use that momentum in our equation to relate energy instead of momentum of the particle. Okay, so we derived momentum in terms of energy, so I'm just going to plug that in now. Momentum is the square root of 2m E minus V. But we want the square momentum, so if you square a square root, you know the square root just goes away, so there's p squared, divided by h squared, times 4 pi squared, psi of x equals 0. So we're almost there. Now we introduce h bar, which is just a variation of Planck's constant. It's much like over here where we relate the radial frequency with the normal frequency by a factor of 2 pi. That's how h bar is related to h. So we have h bar is simply h over 2 pi. So then we have h bar squared is h squared over 4 pi squared. That's all it is. And now we recognize it right here. That is simply 1 over h bar. So we'll simplify that. 2m E minus V over h bar squared psi x 0. Okay, so that's where we are now. Almost there. Now I'm simply going to do some algebra. So I'm going to subtract this and move it over to the right. And while I'm at it, I'll move the h bar. Minus second derivative times h bar squared. So that's just algebra. I'm going to do a little bit more algebra here. 2m goes away. And now we have this form distributing here, E psi of x minus V psi of x equals all this business, minus equals minus h bar squared over 2m, second derivative of the wave function. And that is the Schrodinger equation, right there. And in an even more simple form, if I just move this to the left in the conventional way that it's written, you have this times the second derivative of whatever you're dealing with, which is the wave function in this case, plus the potential times the wave function equals energy times the wave function. Okay, so that is the Schrodinger equation. And what you may have seen that is more familiar to you is simply h bar psi equals E psi. And h bar is just called the Hamiltonian operator, and all that it means is this part right here. That part right there. So I'm sorry, did I say h bar? It's h hat. H hat is the Hamiltonian operator, and it looks like that. So that's h hat. So then finally, writing in the middle of everything, we have h hat psi is E psi. That's the Schrodinger equation. This is what it looks like in detail, and that's how it's derived. I love doing this stuff, so let me know if you have questions. Sorry it's kind of messy a little bit, but doing the best I can with what I got. So, yeah.